The countdown reached 0. The engines ignited. The boosters fired. And Ariane 5 began its first journey into space. Everything looked perfect. For years, Europe had worked toward this moment. A rocket powerful enough to carry heavier satellites, support ambitious scientific missions, and compete in the global space industry. Ariane 5 was more than a rocket. It represented Europe's future in space. But 37 seconds after the flight sequence began, only about 30 seconds after leaving the launch pad, that future was gone. The rocket did not fail because an engine exploded, not because a fuel line ruptured or a structural component broke. The hardware was working. The engines were firing. The rocket was following its planned trajectory. So investigators faced a question that would take weeks to answer. How can a rocket fail when almost everything is working exactly as designed? The answer was not in the engines, not in the fuel, not in the structure. It was hidden inside the software, somewhere inside that rocket. A single number was about to bring the entire mission down. This was Ariane 5 Flight 501, one of the most famous software failures in engineering history. And what makes this story so fascinating is that it was not caused by someone ignoring engineering principles. The failure came from something much more subtle. A decision that was correct for one rocket was carried into another rocket where the conditions had changed. To understand why Ariane 5 mattered, you have to understand what came before it. Since 1988, Europe relied on Ariane 4. It was not the largest rocket in the world, but it was reliable, which is something every space program wants. By the time Ariane 5 was ready, Ariane 4 had established itself as one of the most successful commercial launch vehicles ever built. But Europe wanted more. Ariane 5 was not simply an upgraded Ariane 4. It was a completely new launcher designed to carry much heavier payloads and strengthen Europe's position in the global space industry. It represented years of engineering effort and billions of dollars of investment. This was Europe's next-generation rocket. Its first mission carried 4 scientific satellites called Cluster. Years of work had gone into building them. On June 4, 1996, Ariane 5 stood ready at the Guiana Space Center in French Guiana. The countdown proceeded normally. At 9 hours, 33 minutes, and 59 seconds local time, the flight sequence began. The main engine ignited. The 2 solid rocket boosters fired. Ariane 5 lifted away from the launch pad. The first moments looked exactly as planned. Telemetry showed a healthy rocket. The trajectory was correct. The mission appeared to be a success. But 22 seconds into the flight, telemetry showed something unusual. The system controlling the main engine nozzle began to behave unexpectedly. For a moment, this looked like the beginning of the explanation. Was this the first sign that something mechanical had gone wrong? But investigators would eventually prove something surprising. It wasn't an engine problem. The real failure was still hidden, and it was about to happen. Ariane 5's guidance system relied on 2 identical computers called inertial reference systems. These systems constantly measured the rocket's movement. They calculated acceleration. They tracked orientation. They told the flight computer which way the rocket was pointing. There were 2 of them, one active, one backup. This was standard aerospace redundancy. If one system failed, the other could continue. At approximately 36 seconds after the flight sequence began, the backup inertial reference system encountered an internal software error. The system did exactly what it was designed to do. It shut itself down. 50 milliseconds later, the active system encountered the same error. It shut down too. Both guidance systems were now unavailable. But the computers themselves had not physically failed. They had followed their own instructions. The problem was that those instructions were built around assumptions from a different rocket. The failure started with a single value inside the guidance software, a value called horizontal bias, or BH. Think of it as a number the guidance system used while calculating the rocket's horizontal motion. The software stored that value using a large numerical format, but one part of the program later converted it into a much smaller one. It was like measuring the contents of a swimming pool using a cup. The software had originally been written for Ariane 4. On that rocket, the cup was never filled. Its flight path meant the value could never become large enough to cause a problem. But Ariane 5 was different. It accelerated differently. It built horizontal velocity much faster during the first seconds of flight. The old assumption no longer applied. The code was not wrong. The world around the code had changed. The number kept growing. Eventually, it exceeded the largest value a 16-bit signed integer could represent. One more calculation, and there was nowhere left to put it. The conversion failed, and because that specific error was not handled, the inertial reference system shut itself down. But this raised a bigger question. Why was this software running on Ariane 5 in the first place? When investigators began examining Ariane 5 Flight 501, they were not looking for a careless mistake. They were looking for a reason. The answer led back to Ariane 4. Much of Ariane 5's guidance software came from a system that had already flown successfully for years. From an engineering perspective, that decision made sense. Changing proven software can introduce new risks. Keeping software that has already demonstrated its reliability is often the safer choice. But software contains more than instructions. It contains assumptions, and one of those assumptions belonged to a different rocket. The problem came from a part of the software called the alignment function. Before launch, the inertial reference system needed to determine exactly which direction the rocket was pointing. This process was called alignment. Think of it like calibrating a compass before starting a journey. The system used this information to establish the rocket's exact orientation before flight. On Ariane 4, this alignment function continued running for about 40 seconds after the flight sequence began. There was a reason. If the countdown had been interrupted shortly before launch, engineers could restart the mission without repeating the entire alignment process. The feature had value. It was not a mistake. But Ariane 5 had different requirements. Its launch sequence did not need this function to continue running after liftoff. Yet the code remained. It was carried forward because it was part of a proven system. And this created the critical mistake. The software was reused, but the assumptions behind the software were reused too. Years before Ariane 5 ever launched, engineers had already considered the possibility of numerical overflow in the guidance software. Where they believed an overflow could realistically happen, they added protection. But for the horizontal bias value, they did not. Why? Because on Ariane 4, it could never grow large enough to exceed its limit. Protecting against an impossible situation would have added unnecessary work for a computer with limited processing power. So the software reflected a perfectly reasonable assumption. This value will never overflow. For Ariane 4, that assumption was correct. But Ariane 5 accelerated differently. It reached higher horizontal velocity much earlier in the flight. The assumption had changed. The software had not. The most surprising part of Flight 501 was not that a software error happened. It was that the backup did not save the rocket. Ariane 5 had two inertial reference systems. One active, one backup. So why did both fail? Because they were identical. They had the same hardware, the same software, the same calculations, the same assumptions. When a backup system encountered the overflow 36.7 seconds after starting the flight sequence, the active system was following the exact same path. 50 milliseconds later, it failed for the same reason. Redundancy protects against independent failures, a sensor breaking, a processor failing, or a component wearing out. It cannot protect against a mistake that exists identically in both systems. But the software error alone did not destroy Ariane 5. The next part of the failure chain was even more unusual. When the inertial reference systems shut down, they did not simply stop communicating. In the final moments before shutdown, they sent diagnostic information to the flight computer. This was not normal navigation data. It was information about the failure itself. The flight computer was not designed to distinguish diagnostic data from valid flight data. It interpreted the incoming bit pattern as genuine guidance information. Believing the rocket had suddenly veered off course, it commanded an aggressive correction. The solid rocket booster nozzles moved. The main engine nozzle followed. The rocket obeyed a command based on a problem that never existed. But the correction itself was real. Within a fraction of a second, Ariane 5 entered an angle of attack its structure could not survive. The vehicle broke apart, and its automatic flight termination system destroyed what remained. The rocket was gone. The 4 cluster satellites were gone. And investigators now had to answer a bigger question. How did a software assumption from an older rocket survive all the way in Ariane 5? 9 days after the launch failure, the European Space Agency and NIS created an independent inquiry board. It was chaired by mathematician Jacques-Louis Lyons. Investigators recovered both inertial reference system units from the crash area. That recovery was critical. The systems contained diagnostic information recorded in the final moments before shutdown. Those records allowed investigators to reconstruct the failure. But investigators needed more than a theory. They needed proof. So they recreated the conditions of Flight 501. Using the recovered software and the actual Ariane 5 flight trajectory, they reproduced the failure. The same value overflowed. The same software exception occurred. The same chain of events followed. The cause was confirmed. The inquiry board's conclusion was direct. The failure was caused by specification and design errors in the software of the inertial reference system. Not a manufacturing defect, not a hardware failure. A software assumption that was valid on Ariane 4, but invalid on Ariane 5. After identifying the cause, investigators examined how the failure survived until launch. Ariane 5 had been tested. The components had been tested. The software had been tested. The Ariane 4 guidance system had proven itself through years of successful missions. But the complete Ariane 5 system had not been tested under the exact conditions where the failure appeared. The missing test was a full end-to-end simulation using the actual Ariane 5 trajectory, the real guidance system, realistic flight conditions. The test would have exposed the problem before launch. The system was not untested. It was tested against a different reality. The inquiry board published its final report on July 19, 1996. It did more than identify the immediate cause. It examined the engineering decisions that allowed the failure to happen. The first recommendation was simple: stop the alignment function from continuing after liftoff. The function was no longer needed during Ariane 5's flight. But the larger lesson was much bigger than one piece of code. A component that works successfully in one environment cannot simply be assumed safe in another. Ariane 5 was a different rocket. It had a different trajectory, different acceleration, different operating conditions. The software needed to be validated against the system it was actually controlling. The board issued 14 recommendations. Among them, test complete systems, not only individual components. Use realistic flight conditions during qualification. Review assumptions whenever software is reused. Treat software failures as possible system failures, not isolated programming mistakes. The goal was not only to repair Ariane 5, it was to change how engineers approached complex systems. The failure destroyed the 4 cluster satellites. Years of scientific work disappeared in less than a minute. But the mission was too important to abandon. The European Space Agency rebuilt the satellites. 4 replacement spacecraft were constructed. In the year 2000, 4 years after Flight 501, the rebuilt cluster mission successfully reached orbit. The satellites eventually completed their original mission, studying how the solar wind interacts with Earth's magnetic environment. A mission that ended less than a minute after the flight sequence began was finally completed 4 years later. Ariane 5 was grounded while engineers implemented corrections and reviewed the system. Its second qualification flight, Flight 502, launched in October 1997. It reached orbit, but a separate issue involving the Vulcain main engine nozzle caused the mission to achieve a lower-than-planned orbit. The program continued. The next qualification flight in 1998 was successful, and in December 1999, Ariane 5 completed its first commercial launch. The rocket, whose maiden flight lasted only seconds, became one of the most reliable commercial heavy-lift launch systems of its era. Over the next 2 decades, Ariane 5 carried some of the most ambitious missions in space exploration. It launched Rosetta, Europe's mission to study a comet; the James Webb Space Telescope, one of humanity's most advanced space observatories; JUICE, a mission to explore Jupiter's icy moons. When Ariane 5 completed its final launch in July 2023, it had flown 117 missions, with 112 successful launches. A rocket remembered for a disastrous first flight became known for reliability. But Flight 501 is remembered not because Ariane 5 eventually succeeded. It is remembered because of the lesson hidden inside the failure. Ariane 5 did not fail because engineers ignored safety. It failed because a decision that was correct in one environment was carried into another where it no longer applied. The software worked. The assumption behind the software did not. That is what makes failures like Ariane 5 so difficult to prevent. They rarely begin with something obviously broken. They begin with something everyone believes is still true. A number that was once safe. A function that was once necessary. A design decision that was once reasonable. Until the world around it changes. Ariane 5 taught engineers a lesson that applies far beyond rockets. When you reuse software, you do not just reuse the code. You reuse the assumptions hidden inside it. And if those assumptions are never questioned, they become the most dangerous part of the system. That is the hidden layer